With this lecture, I'm starting a set of lectures on one-dimensional flows, 1D flows. So they're characterized by differential equations. For now, we'll consider differential equations in one variable. So we'll have variable t, which is independent variable, and which is in fact will represent time in all our models. And then we have dependent variable, which we can use notation x. For example, like so, it is dependent variable. It characterizes state of the system, of dynamical system we're considering, and for example, it can represent position of moving particle. On a line, for example. So on for line, we will have only one variable for coordinate. So therefore our equation, so we will have differential equation. First order equation. So in most general form, it will be f of x dot x t equal to 0. Here, x dot represents derivative of f of x over t. So this is common notation in mechanics. The derivatives over time denoted by dot, x dot, and this is called Newton's notation for derivative. So, and solution is x of t, some function, solution. And solution is what makes the differential equation identity. What it means? So it means that if we'll put in x, we will put x of t, x dot of t, x of t, and t, we will have identically equal to 0. So more often people represent differential equations whenever it's possible explicitly. Explicitly means have derivative of x, and derivative of x is given by function of x and t. Furthermore, if we don't have time t, so this is explicit. Form. If we don't have time on the right-hand side, it is called autonomous. Okay, and again, so we have, so generally differential equations have family of solutions, and to specify unique solution, we need to supply it with initial conditions. Initial conditions x at t equal to 0, let's say x naught, makes solution unique. Okay. Now let's consider differential equation x dot equal to f of x, and assume f of x has kind of shape like this. This is x, this is f of x. So what we can see here, there are three interesting points. This, and this. So at these points, I will call it x capital 1, x capital 2, x capital 3. So f when x equals, say, to x capital 1 equals to 0. And this is interesting point. It's very similar to what we had for maps. If, let's say, x naught equals to x1, then x at any t equals to x1. So this is called stationary solution. Stationary solution. It's also called equilibrium point. And it is also quite often called fixed point. Now, what happens? Why, if x naught equals to x1, x will stay, x will not change, because f of x1 is 0. This means that x dot will be 0, and this means that x is not changing. So if we will look at solutions, let's say this is x1. So this is time, this is x. So if x equals to x1, it will not change. So solution will be represented by horizontal line. Good. And same, by the way, with x2 and x3. So this is x2, and this is x3. So these three lines represent three solutions. X of t equals to x3, x of t equals to x2, x capital, and x of t equals to x capital. Good. What happens in between? Assume where x naught is somewhere at this point, somewhere here. Let's make it right. Somewhere here is x naught at time 0. This is time 0. So it is somewhere here. What we see that f of x here in this place is positive. And so here f of x is positive, which means that x dot is positive, which means that x is increasing over time. And increasing over time means that it will go up, something like this. So if it's here, it will be still going up. Here it's also still be going up. So in domain 1. Let's call this domain D1. In domain D1, all orbits or solutions are given by x increasing. On the other hand, although they're increasing, they can't cross x1 because at x1 derivative is 0. So they should, closer they get to x1, slower they will increase. So let's put it like this. Not crossing. Now let's consider what happens when x0 is between x1 and x2. If it's between x1 and x2, it's here. We see that f of x is negative. And here what we have f of x negative, which means that x dot is negative, which means that x is decreasing over time. So this will be like this. And again, although they're decreasing, they can't cross horizontal line x1 because at horizontal line x1 derivative is 0. Therefore, it can't cross. It will stay. As soon as x becomes equal to x1, it will not change. So it gets closer and closer. If it comes, for example, to the value of x1, then it will not change anymore. But it will be getting closer and closer forever. So here we have decreasing. So if we will look at values of x0 between x2 and x3, we will find out that here f of x is positive, therefore x is increasing. It will be like this. So x dot here is positive, and here x dot will be negative. So it will come here. What happened? Just if we know only plot of function of f of x, we already know quite a lot about dynamics in this flow. We know domains where function is increasing or decreasing. We know domains. So this is domain, for example, D2. So if we started, if x0 is somewhere in domain D2, then all our solution will stay in D2. It will never go away. This is domain D3, D4. So we can put it like this. If x0 belongs to domain Di, then x of t belongs to domain Di for any time. So it stays always in this domain. It is first point. And second interesting point, if we look here, we will see that these trajectories around x1 converge to x1. They diverge from x2 solutions in domains D1 and D2 converge to x1. In D2 and D3 diverge from x2. In D3 and D4 converge to x3, and so on. So therefore we have stable and unstable stationary points. We have stationary points of both types, stable and unstable. Now, definitions of stability is pretty much the same as we used for maps. So definition, let's put it like this. Of stable equilibrium. So X is stable equilibrium if for any epsilon there is delta such that if x naught minus x capital by absolute value less than delta, then x of t minus x capital less than epsilon for any time. So this is called Lyapunov stability. It's also called neutral stability. So what it means, there is no convergence. No convergence. Asymptotic stability, let's put it definition of asymptotic stability. Again, X is asymptotically stable if there is delta such that if x naught minus x capital by absolute value less than delta, then x of t tends to x capital while time tends to infinity. So this is asymptotic stability. So we have convergence. There is convergence. So our next point will be about conditions when equilibrium point is stable or not. If we get back to this plot of f of x, what we can see that, for example, x1 was stable. This guy is stable. And it is stable because if x is lesser than x1 at some, that, for example, originally or at some point, then it should increase. Here, x should increase. I will put it like arrow. Let's put green arrow. Because f of x here positive, and therefore x dot is positive, therefore x is increasing over time, and here it's decreasing over time. So here is increasing over time, and here it's decreasing over time. Therefore, x3 is also stable. Yeah, x1 stable, x3 stable, x2 is unstable. So when x is stable, if f of x is negative on this, if for x less than x1, x dot is positive, and for x more than x1, x dot is negative, then x1 is stable. So what it means? It means that with increase of x, f of x is changes sign from positive to negative. And from here we conclude that f of x should be decreasing function. And this is the main point here. If f of x is decreasing at equilibrium x, then x is stable fixed point or stable equilibrium. And other way around, if f of x is increasing at equilibrium point x capital, then it is unstable. And this can be, so this was illustrated geometrically, but this can be proven analytically also. So let's state it as a theorem. So we consider flow. We consider point, equilibrium point x capital. And then we say equilibrium point x capital is stable if f of x is decreasing, which means that derivative of f x equals to x capital negative, and is x capital is unstable if this derivative is positive. And we can put if derivative is 0, that not conclusive. Not conclusive. It is also similar to what we had. Conclusive. Conclusive. So it is similar to what we had for maps. The only difference is for maps we had, just to remind you, by absolute value less than 1 for stability. So this is different. And to prove it now, proving a proof is also very similar to what we had before. So let's start with x naught, which is x capital plus epsilon. Yeah, and like say epsilon naught, or we can put it like this: x of t equals to x capital plus epsilon of t, and epsilon of t, let's say by absolute value, very small. So if it's small, we can use linear approximation. Then x dot equals to d over dt of x capital plus epsilon. So x capital is fixed, but epsilon is function of time, therefore it will be epsilon dot at one hand. Yeah. So x dot equals to epsilon dot, fine, because difference between them is constant. On the other hand, x dot equals to f of x. It is our flow. And this can be represented. We can take its first order approximation. This will be equal to f x capital plus derivative of f over x at x capital times epsilon. And this should be equal, so since x capital is equilibrium, this should be 0. Therefore, what we got here, epsilon dot equals to f derivative of f x capital times epsilon. And for this is pretty much like epsilon dot equals to a epsilon. This can be integrated. I am not showing this. Epsilon is epsilon naught times e to the power of at. Yeah, this is, probably you remember this. So this is solution for differential equation, for this differential equation. And here it will be the same. Epsilon, the function of t, equals to its value at times 0. We can put it like epsilon at t equal to 0 times e to the power of derivative of f over x at x capital times epsilon. So this is our solution. And what it means? It means that epsilon, say, tends to plus minus infinity if derivative of f at x is positive, and epsilon of t tends to 0 if derivative at equilibrium is negative. So this is our conclusion. And if epsilon tends to 0, this means since we have x of t is x capital plus epsilon, which means that x of t will tend to x capital, and this means x capital is stable. And other way around, if epsilon tends to plus or minus infinity, then x diverges from x capital, and x capital would be unstable. So here plus or minus sign depends on sign of epsilon here. So if epsilon at time t equal to 0 positive, then epsilon of t tends to plus infinity, and other way around. Yep. Good. And so this is just to show how it works. So this is x capital. This is our stationary solution. This is time. This is x. So this is convergence. X capital is stable. And divergence, just to illustrate it. Divergence would be, for example, like this. Okay, I will stop here.